Welcome back to Chapter 12, Part 2. In this video, we're going to learn about a very important reaction. It is another carbon-carbon bond formation, so it can help you build bigger carbon skeletons. Very helpful for synthesis, which is a real highlight of this unit. It comes up again and again and again in organic too. So this is a reaction you really need to make sure that you pick up, right? And so it's called a Grignard. Let's be a little less aggressive. Here we go. Grignard reaction. It uses an organometallic. By using a metal, we are able to make carbon into a good nucleophile. So you wind up, first let's prepare the Grignard. Sometimes you might need to do that, depending on what problem you're looking at. To prepare a Grignard is very, very easy. You start with an alkyl halide. Now, most of the time, you're going to see me use a bromine, right? So this can be any sort of alkyl halide. There's a specific one. And I also like that they point this out because sometimes it's hard to manipulate benzene rings, but a bromobenzene can also participate in this reaction. And all you have to do is just introduce magnesium. Now, you may see a solvent, you may not. Notice they're not putting a solvent here. But if you do see a solvent, it'll be something like ether. So 2 ethyl groups on either side of an oxygen. That's going to be really important. We will talk about solvent choice as we move along. You don't need to know the mechanism behind this step. All you need to know is that the magnesium inserts itself between the carbon and the halogen. All right, so in our specific cases, we would have this 3-carbon chain, magnesium, bromine. With our benzene, it would become magnesium bromide. All right, okay. What this does, right, is it changes the typical electron distribution between a carbon and an element it's bonded to, right? Typically, especially with an alkyl halide, you have electron density being pulled away from the carbon. We've seen that being useful in a lot of substitution reactions. But in this case, carbon's much more electronegative than magnesium, and so we're going to get a pull of electrons to the carbon. So we wind up with a carbon with a partial negative. Sometimes this may be drawn in one of 2 ways. You see this here. It is a metal and a non-metal, so you may see it drawn as more of an ionic bond. But you frequently will see it drawn with a covalent bond as well. And then it's a partial negative, partial positive. Either way, it is fine. You see here, Klein's telling you they're pretty much equivalent. It's got significant ionic character, but it can be described as covalently bound. It's very much in the middle. It's a very, very, very polar covalent bond. Now, which way you draw it will somewhat affect how you are going to proceed in the mechanism, right? Whatever you are attacking, so whatever the electrophile is that you are attacking, it's either going to come from the lone pair on this carbon here, or it'll come from the bond if it is shown as a covalent bond, because that's what these electrons are. They were the ones that were being shared between the C and the Mg. That's the only real difference or issue I can think of that you might come across there. So whichever way you prefer to draw it, have at it. Now, the overall reaction and mechanism. How are we going to use a Grignard? Your starting material, and let's start with aldehydes and ketones. Aldehydes and ketones behave the same way. So these can both be R groups, or they could be H's or an R and an H. It's a two-step reaction where you treat with your Grignard reagent. And in the second step, and I will take points off here if you do not put a 1 and a 2, you are going to treat with water. You may see H3O plus being used. That's also fine. It's a proton source, so it might just be water. It might be an acidic solution. But the product is going to be the addition of that R group onto the carbonyl carbon and an OH. All right, so we are going to be making secondary and tertiary alcohols here, depending on if we are looking at aldehydes or ketones. Okay. All right, now, okay, the mechanism. All right. So if we're taking that aldehyde or ketone, I'm just using acetone as my example because I'm lazy and it is the easiest one to use. You can see how Klein would show you the R as an anion. I'm going to go ahead and show you the way you'll normally see me draw it. I usually keep it covalently bound together, but the magnesium and the bromide do not wind up in your product. This is the very first step is where you lose them. All right, so right away, we form this oxygen anion because you cannot have 5 bonds to carbon. And then we've made our new carbon-carbon bond, and it just sits right here. In the second step, when you bring in the water or the acid, that is where you are going to pick up that proton. So why am I so aggressive here about saying that this is a 1-2 step reaction? Because if water is present, it will kill the Grignard. Water will, excuse me, okay. Hopefully I can get through this. Will kill the Grignard. I'm trying to be dramatic here. All right, why? Well, it's a very strong nucleophile, which is what we want. But what sometimes is the case with a strong nucleophile? It's also a strong base. And protons are just easier to pick up. Less steric hindrance. It's it's a fairly weak bond, or meaning it's a very, very polarized bond. It will pick up a proton instead, and it will just make a CH. All right, this is not what we want. There's easier ways of making an alkane than to make a Grignard and then kill it. So if you put them together, you will not get the desired reaction. So if you don't put a 1 and a 2 here, then this reaction doesn't actually work. So you have to put these steps. And that's true for any of the reactions I've given to you that are multi-step. If you don't put the 1 and the 2 and 3 and 4 and 5 or whatever, you're saying that it's all going in the same pot at the same time. And if we've gone out of our way to say it's a multi-step problem, then that is just not going to work. And there is Klein explaining the same thing. So we can see this is a way to make different alcohols. If you are working with something like an aldehyde or an asymmetric ketone and you are going to make a chiral center, it will be racemic because this carbonyl is flat. The Grignard can attack from either side, so you will get a mixture. So stereochemistry is not something to worry about here for me. You could... something that you have to be careful with, what they're showing you right here is this would not be appropriate. You can't make a Grignard with alcohols present for the same reason you can't make a Grignard with water present. They will react with each other. This side will react with this side, and you will not have any Grignard by the time you add that carbonyl. So you would need to protect this, basically block it off from being reactive before you use the Grignard. Protection chemistry is a whole area. You'll learn a little bit more about it in organic too. This is kind of the scheme of of what a protection would look like. I'm not going to ask you to do protections. That's not something that's covered in this chapter. Okay, it's not something I cover in this chapter. There are lots of, again, this is a huge category, and we're not going to spend time in it this semester. Okay, so let's get past the protection. There we go. You may skip protections. Skip protections, please. Thank you. Now, there is one more thing. Okay, to end this particular video, to end our discussion of Grignards, I want to talk about Grignards with esters. You're going to look at carboxylic acid derivatives in great detail in chapter 20 in organic 2. But I do want us to talk about one of them so you can see why it's so important that an aldehyde or a ketone, why I stressed those two functional groups. If you treat an ester with a Grignard, and I'm going to go ahead and say you're going to have an excess amount, just so you know you have plenty, MgBr. And then you work it up, right, with your acid or your water. You are going to get your alcohol, but that R group is going to add 2 times. So the Grignard adds twice. That's because this group right here, it can leave. It's not a great leaving group, but Grignards are really basic, and so it is perfectly okay to lose a base in those conditions. And so if we were to look at that mechanism, it's going to start off very similar. How would I put a B there? Here we go. R, M, G, B, R. We're going to attack and open that up. You always open up that double bond first. So then we're going to have the O minus. We have our O ethyl and our new R group. Now, when this is an H or another R, nothing can happen. A carbon won't leave and a hydrogen won't leave. But an oxygen can leave. So that one will pop off and we'll be left with a ketone. And it will be impossible to keep that ketone from reacting with the Grignard because it's just as reactive as the ester. So now, when we add that second R group, there is nothing that can leave. And so we're stuck until we add in our acid or our water and we get our proton. So that's the big difference between aldehydes and ketones at once. It's worth noting, and that's what I'm going to leave you with. Aldehydes and ketones, the Grignard adds 1 time. For esters, and you'll learn about other groups that behave this way, it's 2 times. And I do expect you to know that will show up. All right, I'll be back in part 3. We'll talk about phenols, etc.